Do you hear me? Do you hear me? All right. So technically we will go through this rotation topic today. On the rest of the semester, we can talk about exams or questions or anything else, or just repeat the things you didn't understand fully. So this last topic is the rotation, and it will be very similar to the incline example. How will a body speed up if it can translate and rotate also on an incline, for example? Let's start at the beginning. So do not forget the origin. Do you see my mouse on the screen? I think yes. So the origin is always a straight line on a circle, which said that theta equals 0 is here. Instead of x, instead of uh, uh, this translational x, one dimension, we use theta, but this is also a one-dimensional motion since we only move on this circle, on this line. The physical quantity we use is the theta. This is the angular position, the angular displacement. If we derive the theta, it will be the angular velocity. If we derive again, that will be the angular acceleration. Do not forget, even if a one-dimensional problem, this motion is in 3D. So for example, if you look at a cylinder that rotates like that, the angular velocity points in that direction. So this is again a right hand rule. The angular acceleration point according to this simple plot, and if we increase the angular velocity, that means it will be longer and longer but point on the same direction. The angular acceleration in this case is parallel with the angular velocity. If we decrease the angular velocity, means we slow down the rotation, the angular acceleration will be opposite to the angular momentum with the angular velocity. There are two kinds of acceleration we can talk about. One is the so-called radial or centripetal acceleration, which is true even the velocity or angular velocity is a constant. This comes from the fact, just a minute, that even the velocity of one point, the speed of one point of the circle is the constant, the speed is the length of the velocity vector. Since it moves on a circle, it changes its direction. So even the v, the absolute value of the v or the length of the v is the same, there is delta v, and if we derive delta v with delta t, we can have an angular acceleration. We can have a centripetal acceleration. Its formula is v square over r, but since the velocity is r times omega, you can rephrase it like centripetal acceleration omega square r. So you know, if it v square over r, if you replace the v with omega times r, here where we have omega square r square, if you derive with r, that will be omega square r. This is the first kind of acceleration, the centripetal acceleration, which is true even for a constant angular velocity. But if we speed up the rotation, if there is angular acceleration, alpha here, if you multiply it with r, you will get the tangential acceleration. The full acceleration of a body will be the vectorial sum of these acceleration. We know from the work theorem that there is a quantity which can be increased by work, and if there is no potential energy, no friction, and nothing else, it will be the 1/2 mv square, the kinetic energy. What is the kinetic energy of the rotating rigid body? It's not easy to calculate because the v, the velocity, technically depends on r, where this point on the body. So let's assume this is a constant omega rotation. The kinetic energy of this small point 1/2 mi vi square, that's different, that depends on the r. So here we have to rephrase again this formula. Let's change the vi to ri omega and take the square, and then just keep outside of the bracket is 1/2. Here we have angular velocity, which is a good physical quantity for rotation because it's true for all of the body, not depends on the r, nothing. This is just something we can measure, and the rest is the so-called the moments of inertia. How we calculate this moments of inertia, it's not easy, but in some simple cases, some mathematical objects, this is, for example, 1/2 mr square, 2/5, 2/3. So it's always mass times r square, and this constant technically describes the shape of the body. We solved one example, another one, and you solved. Oh, were you able to use this Moodle to upload your results? Let me check it. Just give me 1 second. Oh, some of you submitted. All right. Oh, do you have problem with Moodle? Or why? What was the problem with the Moodle? Because some of you were able, so 11, so half of you. So you sent via email. Yes, there are other people send me email. We have to solve the video, but I can't find a question in the book. Oh. All right, so I receive some hundreds of email a day. So if you can't upload it, just do not send me right now because I will lost it. So I will ask and just collect it, put it in a directory in your laptop or somewhere, and I will ask before the test 2 or before the exam, and then you can you can send it to me. So please do not send me one by one. I will ask you if I see that you didn't update anything in the Moodle. I will mail you, or I will send a Neptune message that please let me know what is your result. So I can't guarantee that I do not. Oh, there are other questions. How can I send it to me? All right. Already. All right. I will let them know. All right. Let's talk about torque. Torque plays the similar role in rotation what force plays for translation. So we know, so if you repeat these letters like F, oh no, this is the torque. So this is the definition of the torque. This is a vectorial multiplication. If we rotate in 2D, like if we rotate in the plane of the screen, this torque is, and we have to suppose that the origin is the axis of the rotation. The force that tries to rotate this body starts here. We have to draw a vector from the origin to this action point, and the force is also a vector, so we are in 2D. So this is r, this is force, and we have to take the vectorial multiplication of these two vectors. If we are always in one plane, it's easier to calculate to use this so-called level arm. That means if you extend the vector of the force, that is, this dashed line is the line of action, you have to measure the distance between the rotation axis and this line of action, and this is the level arm. And you can calculate a bit more easy the torque, like F times D, to force, the nominal value of the force, so in this case it's not a vector, and the level arm. If you know even the theta between the force and the vector, this is F times R times sine of theta, sinus phi in this case. Also true that if there are more forces that tries to rotate a body, you have to calculate the vectorial sum of the torque, and this vectorial sum of the torque is like the net torque. It's similar like net force, and this is the Newton's second law for rotation. Torque equal, in this case, is not m times a, but moments of inertia times angular acceleration. The reason the m itself is not enough for describing the rotation, because the rotation depends on the shape of the body. So we have to use this 1/2 for cylinder, 2/5 for full ball, 2/3 for basketball-like balls, and so on. So this is the Newton's second law. In F equal m times a, we use here torque equal moments of inertia times angular acceleration. And at more forces, we had to calculate the net force. Some simple example. So this is a massless seesaw, and we put a body here, another body here, and let's calculate what is the condition for balance. Let's calculate the torque. This is the A vector. So if you want to, calculate the R1 cross FG1, this is the R is the A vector, B is the mass, and you can calculate, you can use your right hand to find what is the direction of the tau1. The torque comes from the mass of, comes from the weight of this mass. So that points towards the U. So from the screen, from the plane of the screen, you have to calculate with the perpendicular vector, and that will be the direction of the torque 1. And since the theta here is 90, sinus 90 is 1, so its nominal value is weight times R1. The condition for the balance is the sum of the torque is 0, so this torque goes towards to U. Let's find out what is the direction of this torque to. Use your right hand, so R2 is this finger, weight is this finger, and if you play the game, play with your right hand, that will show to you that this torque vector will be opposite to the previous one. Its nominal value is, since the angle here again 90, its nominal value is weight 2 times R2, and if we choose a positive direction, which is, let's say, parallel with the torque 1, we can say we can forget the vectors. In this case, this is a positive torque 1, so weight 1 times R1 minus torque 2, which is Fg2 times R2, and therefore the condition of the balance is what you expect. The two torques has to be the same and their direction is opposite. Let's calculate something. So for example, this R1 is 2 meter and M1 is 10 kilogram, and if you put a 15 kilogram here, then the nominal value of the torque 1 is 100 kilogram is 10 kilogram is 100 Newton. 100 Newton. Oh, what is 2 meter? I was not correct. I didn't say where is the 2 meter. So for example, 100 Newton times 2 meter is 200 Newton meter. If you put the mass here with 15 kilogram, that means 150 Newton. What is the R2? In the case that R2 and 150 has to be 200, that's about 1.3 meter. I found a nice example, the ladder example. This is a very nice detailed example. If you have time, you can look at it. What about inner forces? We know there are lots of inner forces, even in your phone, the right end and the left end. I mean, between the right end and left end, there is gravitational force or electrical force and so on. But since the inner forces, since we know the Newton's third law, that if there is a force between two particles, then the force 1 on 2 and the force 2 on 1 follow the same rule. Their direction is the same. I mean, their direction is opposite, but they are parallel. If we calculate the torque comes from the inner forces, the internal forces, that will gives you a net zero torque. That's also an observation. Without external forces, you can't rotate a body, you can't do any angular acceleration on the body. You always need external forces. The internal forces are not enough. Let's calculate some example. We will do it in the seminar, but let's go through the theory. So if there is rotation and translation in the system, we have to use the Newton laws for translation and also the Newton laws for rotation. How can we solve it? Here we have a cylinder and there is a string connected. This mass is capital M, the radius is R, and the mass of this box is small m. We have to suppose that there is forces, so there has to be some forces between these two objects. What we don't know its magnitude, we can also imagine its direction, so there must be a forces on this small m body. that tries to decelerate, and the same body on the other end of the string will accelerate the cylinder. Since they are strongly connected, and let's suppose this is not an elastic string, this is a fixed length string, these two T has to be the same. What is the net force on this M? The net force is the weight minus this right now unknown T. And that's all we can know about this small body. So this body moves like weight minus T equal M times A. What about the rotation? This cylinder has a mass, but since the mass, we always take the mass vector like starting from the center of mass of the body, and this center of mass is the body right now go through the axis of the rotation. If somebody goes through the axis of the rotation, so if there is a mass here, its level arm is 0. So every mass go through, every force go through the axis of the rotation won't give any torque, only this still unknown T will do any angular acceleration. What is the dynamical equation for that? It's pretty simple. The torque, which is this unknown T times R, and since here we have again 90 degree, we can forget the vectors. This is we only have to multiply the length of the torque with the length of the R, and the dynamical equation how it moves is torque equal moments of inertia times alpha. One important thing that in this case, when these are strongly connected, the A and the alpha can't be independent. You can imagine, so if there is any acceleration on this body, this part of the string or this part or the whole cylinder will so-called feel the same acceleration. And acceleration and angular acceleration are connected by the radius, like speed and angular velocity are connected by the radius. That means if you this equation, and this equation, combining it, you can calculate what is the T between the two strings. On the seminar, we will solve one example, and you will see it's pretty simple. One other thing, so that was about kinematics. So if we can calculate the acceleration or angular acceleration, knowing the boundary condition, like where is the body at t equals 0, what is the velocity of the body at t equals 0, what is the initial angular position of the cylinder, what is the initial angular velocity, we can fully describe the motion of the body, like we can give the theta t and the xt. What about energies? Since we are talking about forces and displacement, there must be some work. What will this work does with the body that can rotate on a plane, so and it's fixed, so that means there is no way to transfer energy to potential or translational kinetic energy. In this case, the work, which is energy transfer, will increase or decrease depending the sign of the work, will change the rotational kinetic energy. If, like on this picture, if this barrel can also translate and rotate, the work done by these people will change the sum of the rotational and translational kinetic energy. So the 1 over 2 I omega square plus 1 over 2 mv square. In this case, we have to fix what is the pure rotation. The pure rotation means the wait, perhaps it's not the best. Well, it's a longer. All right, you will understand at the end of the seminar. So pure rotation means so the omega and the angular velocity and the velocity is connected by the radius. This is the pure rotation. Just try to imagine if you look at a car and in dry weather when there is no ice on the road, you can see how the wheel rotates and you can see how the car moves. If you can somehow measure the angular velocity and if you multiply it with the radius of the wheel, you will get the speed of the car. When can it be true? Now try to imagine that this is an icy road and the wheels rotate, but the car does not move at all. In this case, the rotation and the translational motion are not connected. This is the non-pure rolling. So pure rolling is the normal rolling of the bicycle wheel, of the wheel of the car, and if you take a ball and you just push it on the table with not that high speed, it will do the pure rolling. So pure rolling is nothing else, just V equal R times omega. When can it be possible? It's possible only if there is friction. So this is the key point of the pure rolling. For the incline example, we said if the friction is high enough, the body won't move. In this case, is if the friction is large enough, there will be a pure rolling, and if the friction is not enough, that will be the non-pure rolling. So both case the body moves. On the incline plus blocks example, if the friction was large enough, the body didn't move at all. But in this case, the large friction means pure rolling, the small friction means non-pure rolling. We will see you will understand it better by calculating something. Let's go back again to pure rolling. If we are not interested in how the body moves, just want to know something about the body in the initial and the final position, we can use this dynamical picture of the motion. And that's true also if there is friction, I mean the friction is large enough. If this is pure rolling, the potential energy will be transferred to kinetic energy, but not only translational kinetic energy 1/2 mv square, but also rotational energy. Let's go back till here. So what does friction means? Just a minute. In the translation, friction means some part of our work or some part of the potential energy will transform into heat, into internal energy. But this is only in the if the surface of the box and the surface of the and the surface of the floor, these has some relative speed. So when the box moves, so if we push a box on a non-frictionless surface, some part of the energy will be transferred into heat, since these are moving objects and that motion creates heat. But don't forget, the pure rolling means this touching point of the wheel and the touching point of the surface that won't move. That's always fixed. So therefore, for pure rolling, in ideal case, we do not lose any energy that's converted into internal energy. Let's see some examples for pure rolling. At the beginning we have potential energy, and at the end we have rotational, translational, kinetic energy. If this is a pure rolling, means you can replace the V with R times omega. You will have an equation where you can forget the V, you can use R omega instead of it. And if you solve it, you will have a formula like V equal 4 over 3 GH. What does it mean? If we calculate the translational kinetic energy using this V and the rotational kinetic energy using this omega, you can see what fraction of the potential energy transformed into translational kinetic energy and transferred into rotational kinetic energy. And since this is a pure rolling, means the touching point of the object never moves, there is no slipping, no friction of the potential energy transferred into internal energy. We will use example on the next seminar. I will let you know that it's pretty important to have some exercise with this, have some experiences with this exercise. So I will ask you to be online tomorrow to be able to solve it. And we will solve it for enough friction and not enough friction, and technically we will calculate some other things, but technically this is the end of the semester. So let's stop here and we will continue here tomorrow. Do you mind if I start the seminar at 8 because I have an extra lesson from 9? I will. Yes, I will add to you, but at first let's solve it, and then I will give you another example only by changing the numbers. So that's for all today, and I still wait for questions, but stop the YouTube streaming